Okay. So now we're going to talk about reactions of alkenes. So I call this a review. I haven't really gone through the reaction mechanisms yet. But this is something called an electrophilic addition reaction. So it's kind of what it sounds like. We're adding two groups across the double bond, across the nucleophile. If you recall from earlier when I talked about saturation and unsaturated compounds, we recall that a double bond has two less hydrogens than it could potentially have, right? So this is a nucleophile. And you could see how when we remove that double bond, there's like two spots that are open, right? Because carbon here has one, two, three, four things connected to it. If I remove a double bond, it has three things. So when we have a nucleophile, a double bond specifically alkene, and we add HX, where X is a halogen, we'll get something called an electrophilic addition reaction, where we'll add H on one side and we'll add Br on the other side. So for symmetric molecules, it doesn't really matter if I added the H here or here and the Br here or here, because it's the same thing, right? However, that's not always the case. Okay. So let's take a look at this unsymmetric alkene, right? So we get a specific product formed, Cl here, as opposed to this product, right? And we might be thinking, why do we add it here and not here, right? Because once this double bond, once this double bond goes away, we have two open spots, right? So what is the reasoning behind why we add the Cl at this position and the H at this position? Um, it's because of the there's this rule called Markovnikov's rule, which basically says that we will add the chlorine, the halogen, to the most substituted position. So why is this the case? If we look at the pathway of this reaction mechanism, both of them proceed through something called a carbocation intermediate. So this is the intermediate in the reaction, right? And we have a carbocation. A cation is just carbocation is just a plus that's on a carbon, right? This is a more stable structure. And like we were talking about earlier with the reaction free energy diagrams, the thing that's the most stable intermediate will be more preferred, right? So because this plus is more stable on a primary, secondary, tertiary spot versus a primary spot, um, we're gonna add the Cl here as opposed to here. Cool. The reaction produces the more substituted alkyl halide. So let's take a step back and talk about carbocation stability, right? So there's different types of carbocations. There's a methyl cation, primary, secondary, and tertiary. Um, the methyl cation is just a plus on a carbon. Primary just means that you have an R connected to it, R being something carbon containing, right? What we talked about earlier, where the first connection is a carbon and the rest is like some other stuff that we don't care about, right? R. Secondary, two R's, tertiary, three R's. Carbocation stability. Tertiary, secondary, primary, methyl. The more R groups on a carbocation, the more stable it is. Hyperconjugation will decrease concentration of positive charge as the electrons from the sigma bond overlap empty p orbital stability. Um, all this just to say is that these lines here correspond with orbital overlap, right? Because the bond is just orbital overlap. And the more orbital overlaps we have, we get this effect of something called hyperconjugation, which is just something that you get with carbon bonds, right? It's effectively donating extra electron density into this carbon, which is a very good thing. And you don't really have to understand precisely how it works and all the orbital stuff. You just have to know that the more carbons I have connected to a carbocation spot, the more stable that carbocation, this specific carbon, will be because of this effect called hyperconjugation. Okay, so this is what's going on. This is what hyperconjugation is. Again, I wouldn't trouble yourself too much with understanding like the nuances and specifics associated with this. But just, make sure that you have a general understanding of what's going on. All right. A choice between primary and secondary carbocations only forms the secondary product. A choice between primary and tertiary only forms the tertiary product. A choice between secondary and tertiary forms both products. Okay. So a tertiary is more stable than a secondary, but the difference between a primary and tertiary and a primary and secondary are so dramatic that we only form one product when we're comparing between them, versus a secondary and a tertiary, they'll form both products. We'll call one product major and one product minor. So the tertiary spot will form the more stable compound. As we just talked about, it goes through a more stable intermediate. Therefore, it'll be the major product. Okay, cool. So, what does Hammond's postulate say? Hammond's postulate states that the transition state is more similar in structure to the species to which it is more similar to in energy. So that's just to say that this transition state here is closer to R, right? Like this distance between here and here is a lot less than this distance, which means that this transition state will look a lot more similar to the reactants than to the products, versus this transition state is going to look a lot more similar to the products than the reactants. Transition state resembles the reactants, transition state resembles the product. Okay, so practically speaking, applying Hammond's postulate. In an electrophilic addition reaction, the more stable carbocation, the more stable transition state is formed faster, smaller activation energy. Cool. Regioselectivity. So electrophilic addition reactions are very regioselective. So what does regioselective mean? Regioselective just means there's a region for which we select, right? So if we look here, this would be formed from a primary carbocation. This would be formed from a secondary carbocation. It's regioselective because there's a region for which it selects. Here is an example of something that's also regioselective, but moderately so, because it would rather form here. There's a region that this Br would rather be on, right? For here versus here. Okay. Sorry about that. HBr. Okay. So we can see here that both these carbons are like basically the same spot, right? Secondary, secondary. It's a completely symmetric molecule. There's no region for which it would select, right? Because these two molecules are literally the same thing. So that's why both produce secondary carbocations, 50%, 50%, not regioselective. Okay, Markovnikov's rule helps you predict electrophilic addition reaction products. The electrophile, it's usually H plus, prefers to add to the sp2 carbon bonded to more hydrogens, right? Cool. Okay, these are some just example problems. Um, okay, nothing really to call out there. Okay, so we talked about adding H and a halogen, Br in this case, across the double bond. So what are some other things that we can add across the double bond? We can actually add water across the double bond, H and OH, H2O, right? So you need a catalyst for this, okay? Because without a catalyst, this reaction doesn't happen. So we're going to be doing something called acid catalyzed addition of water across an alkene. So basically what's going to happen is you're going to form H3O plus, okay? Whenever you add a strong acid in water, you form this hydronium ion, H3O plus, okay? So this double bond can now attack this because this is a better electrophile, right? Because H2O, you learned earlier that it can be a nucleophile, it can be an electrophile, but it's not really like great at either of them, right? So the reason why we put an acid is to make this a better electrophile, right? Because now we have a plus on the oxygen. This oxygen is trying to pull electron density from these, so we can grab a hydrogen, and then these bonding electrons become a lone pair, right? And now because of that, we've turned this nucleophile into an electrophile. And even though this was considered a weak nucleophile, it's strong enough to attack this position because this is a strong electrophile, right? So throughout this course, you're going to get a trend of like, sometimes when we need to catalyze a reaction, we have both a bad nucleophile and a bad electrophile. So we make one better. And by making that one better, we take a step. And then now we have something that can do this, right? And then by the end, we have our regenerated catalyst, right? The idea of a catalyst is that it gets regenerated throughout the like reaction. It's not used up. And this is our final product. Cool. Addition of alcohols. Okay. Addition of alcohols. So, what you'll find throughout this course is that alcohols and waters react in very similar ways. Okay. So instead of an OH, we're going to have an OR. Okay. So this point, we're going to attach an OR. This point, we're going to attach an H. Right. Why do I attach an H here? This is what Markovnikov's rule says. And again, the mechanism is going to be pretty much exactly what you saw previously, except instead of having an H here, you're going to have an R here. And because of that, we're going to attack here. So there's not that much nuance to it. The reaction will produce the more substituted ether, um, what we saw earlier. Okay. So now we're going to talk about something called carbocation rearrangement, right? So when we have our alkene, this double bond attack an H and a Br, it goes through this intermediate, right? So there's two things that could happen. One could be the BR goes here, right? But this is actually a minor product, and this is the major product. This is because of something called a hydride shift, a carbocation shift. So if we have a plus and we have one bond away here or here, a position that's more stable for the carbocation to be on, this plus will shift to that position. And the plus is not the thing that's moving, right? Because recall that plus is just something that we say to indicate that we have an absence of something, right? Electrons move, bonds move, pluses don't. So what's happening here is this hydrogen is actually moving here. That's why we get a plus movement, like this movement of this plus. Um, cool. Um, I know it's like kind of seems stupid to comment on that, but it's a really important difference, right? It's like one of those things that's just is like a nuance and like really making sure you understand what's going on. Okay. Um, Hydride, H minus. Cool. We never rearrange to a less stable carbocation or something to equal stability. Okay. So we're only going to get a shift if we're arranging to something that's more stable. Because here we have a plus. This is a secondary position. We can go to a tertiary position. We're not going to go from a secondary to another secondary. And if this is tertiary, we're not going to go from a tertiary to a primary or a tertiary to a secondary. Right? Cool. Um, Yeah, I mean, the only other thing I guess is that if this wasn't a hydrogen and this was a methyl group, we can get something called a methyl shift, which is when one of the methyls shifts from here to here to put the plus here. Okay, cool. Hydroboration oxidation. So this is one of the first, I think, like really challenging mechanisms that you'll learn. Um, so what this is doing is it's adding an H and an OH, which we saw already how to do. The difference is it produces the less substituted alcohol, right? Because we learned how to do this with H2O in acidic conditions, but we learned that the H would add here because of Markovnikov's rule, and the OH would add here. So why are we adding an OH here? Okay, so let's take a look at this. First of all, this is just some notes on the solvent, THF. This THF stands for tetrahydrofuran. I don't know if you'd be asked that, but that's its full name. It's a very useful solvent in practical organic chemistry. Okay, step one. This is a conserved mechanism, so all the steps are happening simultaneously. Okay, so this doesn't go through a carbocation mechanism, so it's not subject to the rearrangements that we just talked about previously. So what's happening is that this side of the double bond is attacking this B, which is an electrophile, okay? And immediately this is attacking this here. So it's kind of like a cycle thing, right? So in our transition state, we're making this like kind of cyclic, like one, two, three, four membered ring, right? Which isn't actually what's going on, right? Because this is the transition state, it's not an intermediate, but this is what's happening, right? And the reason why we have the B attached here and not here is because this transition state is more favorable, so it'll form faster. And this has to do with less steric strains. It just has to do with the fact that this is just a more stable structure. We can also use 9-BBN instead of borane. The only thing to note is that after one hydroboration reaction, BH2 still has two hydrogens and continue to react with two more alkenes, yielding Br2. So what am I saying here? Okay, I can't find a good example of it, but basically, hydroboration, oxidation. So we're not on the hook for step two of this mechanism. You just have to know that you should understand this transition state, why we add the way we add, and once we get to here, if you memorize the reagents, this is sufficient. Okay, there's some product predictions here, and then keep note that you have methyl shifts or hydride shifts to move the plus to a more stable carbocation. Only for H2O, H2SO4. We don't have that for hydroboration oxidation because it doesn't go through a carbocation intermediate. Okay, cool. So let's now talk about the halogenation of alkenes. Okay, so halogenation of an alkene. This reaction produces something called a vicinal dihalide. So that just means that we have one line and we're adding the Br across the double bond. So I have a Br here, a Br here, di, two, halide, halogen. Okay, cool. So this is the mechanism. So it goes through this three-membered ring. Okay. So this is a little bit, funky the first time you see it. So let's unpack this, right? So the first thing that's going to happen is this double bond is acting as the nucleophile. So we're going to attack one of the BRs. And then we're gonna get this weird effect of like once we attack this BR, we'll kick off this bond, and this BR will immediately attack back to this two position. So that's why I have two connections here, right? Because I'm attaching here, this gets kicked off, and then I'm using this lone pair to attach here. Okay. From there, the nucleophile will attack the position right here, and it'll open up this ring, and we'll be left with this structure. So what's going on here? First of all, there's no carbocation rearrangements because it's a conserved mechanism. The exact same mechanism works for Cl2. Fluorine doesn't work and iodine doesn't work. Fluorine is just too violent. Iodine is thermodynamically unstable. And regions have to be a solvent, which is anhydrous. Anhydrous means no water. And that's just because if we don't have an anhydrous solvent, then the position that gets attacked here will be attacked by a water molecule and not this. Okay. Formation of a halohydrin. Halohydrin means that we have a halogen. Hydrogen means hydrate. Hydrate means water. So we're adding an OH and a Cl. Okay. And the reason why we say halo or hydration is because we start by adding an OH2, H2O, and then we remove a hydrogen. Okay. So what's going on here? So the first step of this is the exact same thing as the earlier one, right? So this, I said, has to happen without water. This is what happens when you do have water, right? So it's the exact same thing. The only difference is that we attach the water here instead of adding a Cl. And now we have to talk about regioselectivity, right? Because here we were attaching two same things to both these positions. So we're just like, okay, like it's the same thing, that same group we're attaching, so we don't really have to care because, irrespective of which one goes first, like the final product will be the same, right? But now for product prediction, we do care. And we'll actually end up attaching the H2O on the more substituted carbon because the transition state is more stable. That's all it is. Cool. What's happening here is that this bond, this three-membered ring is so unstable, it's actually breaking before this even attacks. So with that, we're forming a partial positive here that's greater than the partial positive that would be formed here because this is the more stable position to form a partial positive. It's a more stable carbocation position. Okay, cool. So this applies for other nucleophiles too. Alcohols, haloethers, halogens. The nucleophile in the reaction above is nucleophilic because it's in the greatest concentration. So if you think about what's going on here, like this is in water, right? So there's like millions and millions and millions of water molecules versus there's only like one equivalent of this reagent, right? So probability says that if we have water, the water is going to attach here. Okay. So that's why we don't do this with water because it's just a probability effect. There's just gonna be so much more water than there's gonna be Br2. So it's just more likely to happen. Okay. Addition of a peroxy acid. So this is something called epoxidation. So an epoxide is a three-membered ring where you have a carbon, carbon, and an oxygen. Um, you're not really on the hook for the mechanism, nor are you really on the hook, generally speaking, for the actual reagent. Sometimes it's, tested as like a one question, like, oh, what is this reagent structure? But in 109B, 109C, like, you never really need to know this. You just need to know when you have MCPBA, it goes from a double bond to this epoxide. This is the peroxy acid. This is the MCPBA. This is the reagent that we use. This is the mechanism. Again, I don't think you're on the hook for this. But basically what's happening is this double bond is attacking this oxygen. This bonding electrons are moving here. This double bond moves here. This bond moves here. And it's pretty complicated and honestly pretty out of the scope of this class to truly understand before you learn a little bit more about organic chemistry. So I think it's sufficient to say that as long as you realize that if you have MCPBA, a peroxy acid, where basically you just have this carbonyl O and then two O's in a row with a double bond, you're going to make an epoxide. Okay. You generally don't even care about the carboxylic acid byproduct. Okay, cool. Adding ozone to an alkane, oxidative cleavage slash ozonolysis. So ozonolysis is another thing that you're not really on the hook for the mechanism of. It's a two-step reaction mechanism. We have this reagent CH32S, which cleaves alkene double bonds. We produce two ketones slash aldehydes. No carbocation, no rearrangement. Okay. Again, you don't need to know this mechanism. All you need to know is that when you see a double bond, you cut this and you glue oxygens on both sides, like they're band-aids, right? Like you make a cut, you put a band-aid on either side. Cool. make a cut, you put a band-aid on either side. Um, and again, these are other reagents that you can use. Basically, every time you see O3 minus 78 and something else after that, you can kind of bet that it's going to be ozonolysis. All right. They're not going to try to trick you. This is a ketone. This is an aldehyde. A ketone is when we have a C double bonded to an O, R's on both sides. An aldehyde is when we have a C double bonded to an O, R on one side, H on one side. And remember, R is just, carbon and then a bunch of other stuff. Cool. Catalytic hydrogenation. So this is reduction of alkenes. So we're adding hydrogens to an alkene. Um, so we talked about adding stuff across a double bond, right? We added H, we added OH, we added BRs, we added, alcohols. So now we're just going to add two H's, right? All that's happening here is I'm removing the double bond because once I remove this, it's not saturated. I'm saturating it with hydrogens. Cool. And you're not on the hook for this mechanism. Just memorize the reagents and what it does. That's sufficient. Cool. Stability of alkenes. This doesn't really have anything to do with this. Like that's all to say on catalytic hydrogenation. So this is the most stable compound. This is the second most stable. This is the least stable, right? And it has to do with the substitution. This is a tertiary spot. This is a secondary spot. This is a secondary spot. This is a primary spot. This is a secondary spot. This is a primary spot. The more substituted alkene is the more stable alkene, right? So when we get a reaction, since we have something that's more stable, we have a lower change in energy between these two. Cool. Okay. Um, yeah, so this is just the reaction plot that corresponds with each of these. We can see that the difference between one and the final product is the smallest, which is why the change in energy is the least. Two in the final product, three in the final product. Cool. The more substituted the alkene, the more stable it is. Okay. So this is a stability trend, and I'll leave it as like exercise to the reader for you to go through and make sure this makes sense. Okay, regioselective, stereoselective, and stereospecific reactions. Okay, so this section is notoriously confusing. Okay, so take the time to kind of slow down and really try to understand what's going on here. Um, Not to say that you shouldn't understand everything else that's going on, but All right. Stereochemistry is the structure of a molecule in 3D. R and S indicate something called absolute stereochemistry. E and Z have sister trans relative stereochemistry. So what does that mean, right? This means that for E and Z, like you have to have one group relative to another. Let me see if I can find a. All right, I'm not finding a very good picture, but recall from earlier when we talked about E and Z, we are like, okay, this thing is opposite to this thing, therefore we have E, right? Like you're comparing one thing to another thing. It's one thing relative to another thing. Versus absolute stereochemistry is you're just looking at one carbon and the four groups surrounding it. Okay. Regioselectivity, we preferentially form one constitutional isomer. We form the one that is um, more substituted. Stereoselectivity is preferentially forming one stereoisomer over another. Um, so regioselectivity, you saw that you prefer a triple bond to a double bond, all of that. Stereoselectivity, we prefer a specific 3D orientation to another, right? This is down the plane, and then this is up in the plane. Okay, sorry. So stereospecificity is a little bit harder to understand than regioselectivity and stereoselectivity. So stereospecific specificity means that you consider the reactant and the product. So first you consider the reactant. If the reactant can exist as a stereoisomer and each stereoisomer of the reactant forms a different stereoisomer or set of stereoisomers for the product, then the reaction is stereospecific. So what is this saying here? This is basically saying that if you have stereo centers in your first like reactant and those reactants preferentially form specific stereo centers in the product, then you have something that's stereo specific. Okay. So this is saying like an E alkene produces product A Z alkene produces product B. So different stereochemistry in these two will allow you to get a different product. Okay. So that's what stereo specific means. Basically, the reactant and the product are important. Stereochemistry of EARs. Reactions that form one asymmetric center. We have the addition of a hydrogen halide. Okay. So we form one stereocenter here because we attach a hydrogen here that already has a hydrogen. Or sorry, we attach a hydrogen here, right here that already has a hydrogen. So we have two groups to the same thing. So it's not a stereocenter. So we only form one stereocenter because this is different. This is different. We have a hydrogen, different, Br. Cool. We get something called an inversion of stereochemistry. Um, sorry, I don't know what I'm saying. We can attack from the top or the bottom, which means that we get both of these, right? There's no specificity. If the reaction has no asymmetric center and forms one asymmetric center in the product is racemic. This applies to all reactions that form carbocations, acid catalyzed hydration, acid catalyzed addition of alcohols, addition of hydrogen halides. Reactions that form a second asymmetric center. So this means you start with a symmetric asymmetric center and you put another one. Um, so let's take a look at what's going on here, right? Okay, so you see here that we're starting with a molecule that's the same. The only differentiating factor is this R and this is S. Okay, so we see here that this forms a different 3D structure than this, right? We have an R and an S. We have SS, SR. So because the S gives a different set of diastereomers from the R reactant, the reaction is stereospecific, okay? So because I got different products from these two things, which are the same, except they have different stereocenters, I have stereospecificity. Okay, reactions that form two asymmetric centers. So here we have no asymmetric centers, and now we form two asymmetric centers. Okay, so if we go from no asymmetric center to a symmetric center, then we can form both enantiomers of this product. Okay, and if we form two stereocenters, we could have a total of 2 squared equals 4, right? And this is like the chart that we go through, right? Because we add here, we could have added both ways. We add here, we could have added both ways. So there's four possible products. Okay. And syn addition is when two substituents added on the same side of the double bond are the only two products that are formed. Okay. So here you have both these groups added on dashes, both these two groups added on wedges. Okay. This is something called um, anti because the things that we added a Cl and we added an H, right? So this Cl is opposite to this H. So sorry, ignore what I said earlier. This Cl and this H are opposite to each other, right? Because those are the two groups we added. So that's why it's anti, because one is up, one is down. Anti, one is up, one is down. Here you see Cl and H are both on the same thing, right? Both are on dashes. We can see here that both are on wedges, so those are syn. Cool. Okay. Anti-addition reactions. So this is addition of a halogen. Let's take a look at what's going on here. So let's start by zooming into this mechanism, right? So we talk about what's going on in this mechanism of we're attacking here, this is being kicked off, and this is attacking back, and we're getting this three-ring structure. And then we have a nucleophile attacking either this position or this position, and then kicking up this Br. So this is an example of an anti-addition because however we do this, the nucleophile and the Br are on opposite sides, right? Because this is up in the plane, okay? And we're attacking the bottom. So we're attacking under the plane, down in the plane. So no matter how you look at it, this BR is up, this nucleophile is down. This nucleophile is down, this BR is up. They're opposite in direction, they're anti. Cool. If we look here, we have regioselective addition, right? We're adding halohydrogen addition. We're adding a Br and an OH across a double bond. And if we look here, we see that we have Z configuration maintained from this. We have E configuration maintained from this. So this is stereoselective, stereospecific. Okay, I'll leave it to you guys to go through the rest. But basically, again, we have something that's cis here, trans here. Transalkene with same substituents forms a meso compound in addition reaction. What is a meso compound? A meso compound is a compound with a plane of symmetry. So this is another example of something being stereospecific, right? Because cis forms different products than trans. Okay, these, you know, regardless of this versus this, Br2, Br2, H2O, they both form anti-addition products because the Br and the Br will be on opposite sides. HO and Br will be on opposite sides. Cool. Okay. Syn addition reactions. Okay. So syn addition reactions are both groups are added to the same side, anti different sides. Okay, we kind of already talked about this. These are the syn addition reactions. These are the anti-addition reactions. Here we can see why this hydrogenation reaction is a syn addition. Cool. Epoxidation is a syn addition reaction. Again, you're not on the hook for this mechanism generally, but remember that it is a syn addition reaction, so these two lines will have to be the same. Okay? Cool. Hydroboration oxidation reaction is a syn addition reaction, and we can look at the transition state, which you're probably on the hook for, and this mechanism, and we can see why it's syn addition. Cool. Okay, so these are all the alkene reactions we've covered so far, right? And they're all pretty similar. They start with the same compound, and we have like a lot of similarity between them, but there's also a lot of important nuances, okay? This CH2Cl2 stands for an inert solvent. So it's basically a solvent that is not nucleophilic. This is a solvent that is nucleophilic, which is why we get two different things. If you don't see this solvent and you just see Br2, you're gonna get this product, okay? They're not trying to trick you. Okay, ring expansion and contraction. Okay, so this is the final thing about carbocations. So with carbocations, we can shift methyl and hydrides to put this plus in a more stable position. The other thing that we can do is we can actually shift bonds. So this bond here can swing open and connect here. So this connection is severed here, and this blue connection moves from here to the green connection, right? So we have this structure, and because we lost a connection here and we gained one here, we lose this plus here and we gain a plus here, right? So again, that's what's going on, right? This plus isn't shifting by itself. It's shifting as a result of what's going on here. 1,2 alkyl shift. We can do this to move this plus to a more stable position. We add the Cl here, right? So there's a lot more going on here than, you might initially think, right? You might think at first like, oh, like, I just add the Cl here, the H here, cool, we're done. But not quite. So ring contraction is on a 7 or 8 membered ring. We do this to decrease ring strain. Okay, so expansion will happen when you have anything lower than 6 and contraction will happen when you have anything lower or anything greater than 7 or equal to 7, right? So 6 is the optimal number. We'll get ring expansion and contraction accordingly to try to get to a 6 membered ring. One, two, three, four, five, six. Cool. Propose an arrow pushing mechanism, draw the major product, right? So just keep note that we have a 3 membered ring, it expands to a 4 membered ring. We have a 7 membered ring, it contracts to a 6 membered ring. And some people ask about how, like, oh, like, can you get multiple ring expansions in a problem? Theoretically, yes, but I've never seen it happen. So I think that it would be sufficient to assume that it doesn't really happen. Um, yeah, and that wraps it up for this chapter. So I know this was a really long chapter, and I did cover the information relatively quickly. So make sure to go through this a couple times and make sure that you have a good understanding of these chapters, because these are very foundational in the scope of what you're going to learn the next chapter, the chapter after that, and just organic chemistry in general.